Hello and welcome to the video covering Unit 4-2, where we actually learn the definition of the Laplace transform. So you may have been wondering, uh, like, where did that table of values of Laplace transforms come from? Well, in this video we're going to hopefully clarify how to compute the Laplace transform. So let's begin. It's called an integral transform for a reason, because it takes a function and you integrate it in some fashion. Notice here we're going to multiply it by e to the minus st, and we're going to integrate it from 0 to infinity. So this is what's known as an improper integral. You're going to need to remember from Calc 2 how to handle those. We'll see just below how to proceed with that. But so this is the definition. So it'll usually be incumbent on you as you're integrating to find the s values for which the integral converges, and we'll talk about that in more detail as we work through these examples. But a couple remarks here, first of which is that you'll notice the integration variable is t, so that means that s right here, that s value, gets treated like a constant. So I'll put treat s like a constant, because with respect to the integral doesn't know that s is a variable, right? Like you're integrating with respect to t, so all the integral knows is that s is going to be treated like a constant. Okay, so let's do a very simple Laplace transform. This is going to be the Laplace transform of just 1, okay? And the function f of t equals 1. So here we go. Follow the definition. You integrate from 0 to infinity, e to the minus st, and then you multiply by the function, which is 1 in this case, right? And now here's what makes this an improper integral is the infinity up here. So I think in Calc 2 we used to put t's, but notice t is already being used, so we're going to use a capital N. So we get the limit, capital N goes to infinity, integral from 0 to n, e to the minus st times 1. And now the antiderivative, this is e to the kt class. So the antiderivative is 1 over k e to the kt. So you notice here is the k value is negative s. So e to the kt divided by k. And now this vertical bar is the same as the notation that I use for like square brackets with the numbers. So like I would probably write this as limit n goes to infinity and then put it in square brackets. So it means the same thing, right? And you'll see as I work through examples that I'll be using the more familiar notation from calculus. Okay, and what we're going to do is we're going to plug in n. Now remember, t is our variable here. S is treated like a constant. So n gets plugged in for t, right? As does 0. So that's where these values come from here. And now let's see here. So this, you'll notice this part right here has no bearing on capital N. So in fact, this is just, notice the double negative, positive. Now e to the 0 is 1 over s, right? So that's where this 1 over s comes from. Whereas here, this, as n becomes large, well, it's going to depend on what s is. Notice s cannot be 0, right? So that's our first observation. S cannot be 0 because we're dividing by it. But furthermore, if we want this integral to converge, and this is what I was talking about before, where it's going to be incumbent on you to determine what s is. If we want this integral to converge, this term better go to 0, right? It better be finite at the very least. But because we're dealing with exponential functions, there's only two options. Either it goes to 0 or it goes to infinity. In order to get this term to go to 0, we know that n is very large and positive. So that means that negative s better be negative, which is to say that s better be positive. And that's where this comes from. So not only can s not be 0, s has to be positive. And so that leads us to this conclusion right here. So when you compute these integrals by hand, when you find Laplace transforms by hand, you'll not only find the Laplace transform, but also you'll need the condition on the variable s. Okay, so let's move on. let's do this one together. So let's compute the Laplace transform of e to the minus 4t. So here we go. We get the Laplace transform e to the minus 4t. Well, by definition, that is the integral from 0 to infinity e to the minus st times e to the minus 4t dt. And now the hint here is first to combine the exponential factors. So we get integral 0 to infinity e to the minus, and now bear with me here. Notice I can add the power, so I get minus st minus 4t as the exponent of e, and then I just factor out a negative and a t from both, right? So here's the negative factored out, here's the t factored out. And I encourage you to check this to make sure these two things are the same. All right, so now we're doing an improper integral. So this is the limit n goes to infinity, integral 0 to n, e to the minus s plus 4 quantity times t dt, which is the limit n goes to infinity. Well, this is e to the kt, right? Remember, s is treated like a constant, so negative parentheses s plus 4 is a constant. And so this is e to negative s plus 4t all over negative parentheses s plus 4. Okay. Well, now this equals the limit n goes to infinity. Well, plug in n, so we get e to the negative parentheses s plus 4 times n all over negative parentheses s plus 4 minus e to the negative s plus 4 times 0 all over negative parentheses s plus 4. You'll notice this is just e to the 0 here, which is 1 on the numerator. I get a double negative. So this is the limit n goes to infinity, e to the minus s plus 4 times n all over negative s plus 4 plus 1 over s plus 4. And you'll notice that this second part here, this second term, has no bearing on n. So you can keep it in the limit or you can take it out. I just chose to take it out of the limit, right? Because it's not going to change with n, and the limit won't affect it either way. Okay, now let's talk about this right here. So remember, n is becoming large and positive, right? So that's a large positive number. So in the numerator, we have e to negative s plus 4 times a large positive number. I want this to be finite, which means that it needs to go to 0. So what I'm going to require is that negative s plus 4 has to be a negative number, which is to say that s plus 4 has to be a positive number. So this is going to give us then, with that assertion, just s plus 4, as long as we're asserting that s plus 4 is positive. Okay. Well, this you can just solve around by subtracting 4. You hit s has to be greater than negative 4. Okay. So the Laplace transform of e to the minus 4t is 1 over s plus 4. And our condition now is that s has to be greater than negative 4. Okay. And you can actually check this on the chart. I've provided one in this section too, way at the very end here. So we had e to the negative 4t, where so c value is 1 here. So we get 1 over s minus negative 4. Is that what we got? Yeah, it is, right? 1 over s plus 4 is the same as 1 over s minus negative 4. All right, so in the next video, we'll do a couple more computations. But this is just a gentle introduction as to how to use the integral definition of the Laplace transform.